Hello class, this is a continuation of direction or slope fields. In this video, we'll be looking and learning how to sketch slope fields. So previously we saw that the solution to differential equations has a plus c, and because of this, we cannot sketch an exact sketch of the original function. We just learned that a slope field represents all the tangents for all possible values of c to the solution to this differential equation. So rather than guess what the possible solution to plus c might be, we just instead sketch all possible tangents to this differential equation. So to sketch the direction or slope field of a differential equation, we just simply substitute values of x and or y. So if a differential equation has only a single variable, x or y, we assume the same solution for all y or x. This will make a lot more sense when we get into our first example here. Okay, so we're going to sketch the slope field for four different differential equations: 1, 2, 3, and 4. But for this video, we'll just stick to the first example here. So we have a differential equation 2x plus 3. We know that the solution to this would be x squared plus 3x plus c. But because we don't know what c might be, we're going to draw a slope field. Okay, so for this, we're only going to be focusing for now on one row of values for y. Notice how there are no y values to substitute in the differential equation. Don't mistake that y prime is not y. Y prime is the derivative. Okay, so for this, we simply substitute negative 3 into x. So we get negative 6 plus 3. That would give us a derivative of negative 3. Then we go negative 2, substituting in. That gives us negative 4 plus 3, which is negative 1. And we continue in this manner, substituting all values for x into the derivative for assuming the y equals 3. We'll do it just for this one row. So 1, substituting in, we get positive 1. Substituting 0, we get 3, 5, 7, and 9. This is simply just substituting x values into the derivative. Now, what this means is at the point negative 3, 3, which would be negative 3, 3. So at this point, okay, the tangent would be negative 3. Okay, so negative 3 would be a tangent. So now at this point, it's hard to draw an exact sketch of what a tangent of negative 3 might be. But for my iPad, this is, well, the iPad for me draws perfect gradients of negative 1. So negative 3 might be something like this. This is really just a guess. I don't know exactly what that might look like, but that there is a gradient of negative 3. At the point negative 2, 3, so negative 2, 3, at that point we have a gradient of negative 1. So sketching that, be something like this. Then we keep going. At negative 1, 3, negative 1, 3, we have a gradient of 1. So sketching that once again, be something like this. And we continue in this manner. So at 0, 3, at x equals 0, y equals 3. So at this point, we have a gradient of positive 3. So trying my best to make it look kind of like this, but in positive. So it'd be something like this. That looks about right. There we go. Then we just simply continue. At 1, 3, x equals 1, y equals 3. We have a tangent with gradient 5. So that's very steep. So at 1, 3, we have a tangent of 5. So make it slightly more, I'm going to rotate it to make it slightly more steep, like so. At 2, 3, we get a gradient of 7. So 2, 3, we get a gradient of 7. So it's very steep now. Something like that. There we go. And we saw that lastly at 3, 3, we get a gradient of 9. It's really, really steep now. So let's duplicate this. At 3, 3, we get a gradient of 9. And I hope you can see that there's a pattern happening, that the further to the right it gets, it's getting steeper and steeper. So eventually it's going to look almost indistinguishable from a vertical line. But we know that it's not a vertical line, it's just getting very, very steep. And you can probably see a pattern forming here, that if we go to the left, it would mirror these gradients. So for example, if we were to go one to the left, because our table stops at -3, if we were to go to x equals -4, we should get a gradient of -5 on the left hand side. So it would be more steep like this. Then if we were to go again, you get more steep, mirroring this one. Oops. Let's try that again. It would mirror, be -7. And one more time, it would be -9 for the last one to the left. But that is just for the row at y equals 3. But because there's no y value at all to substitute in the differential equation, we just assume that every other row is the exact same. So it'd be something like this, which would mean that these derivatives would be the exact same at, for example, at -3, 2, it has a gradient of -3. So at -3, 2, the gradient drawn here must be the exact same as this one. And likewise for every other gradient. So if you were to just copy, well, if I could just copy this, move it down, it'd be the same. And I keep moving it down like this, and so on. And so on. So this is the slope field for this range of x and y values. So let me just finish this off. Whoops. Fortunately for me, I can use an iPad. Unfortunately for you guys watching, you may have to draw this by hand. So that is the slope field for this particular differential equation. I've actually drawn it here. If you take a look, there we go. Now this one is drawn for every half intervals. So notice how we have x equals -1.5, and we can see that x equals 1.5. There's definitely a turning point at that point there, which it doesn't quite show, but we know that at x equals 1.5 there should be a stationary point at that x value. Okay, so I hope that gave you an insight into drawing slope fields. We'll get into more examples. You can begin the exercises at any time you like if you understand them. But hope to see you in the next video, and best of luck.